Что, давайте продолжим.
All right, I would like to continue right now, and I would like to introduce our speakers. Oleg Troshechev, the lead scientist, the chief scientist at the Department of Geophysics, State Research Center of the Russian Federation, the Arctic and Antarctic Research Institute. Yuri Bubiev, Deputy Director of the State Scientific Center, Medical Biological Problems of the Russian Academy of Science. Artemy Goncharov, the head of the Laboratory of Functional Genomics and Proteomics of Microorganisms at the Institute of Experimental Medicine, and Dmitry Chechen, the senior researcher at the Obukhov Institute of Atmospheric Physics of the Russian Academy of Sciences. The floor goes to Oleg Troshechev. Please, the floor is yours. All right. So my presentation is going to touch upon a different topic, namely the monitoring of cosmic space weather. What is a space weather? Space weather is determined by the impact of solar radiation on the Earth. The main agents of solar impact are ultraviolet, thanks to which we are alive, as well as solar plasma, which is coming from the whole surface of the sun, and solar protons, which are related to active zones on the sun. Thanks to having a magnetic field on the planet, we are able to live on Earth, because if we did not have the magnetic field, there wouldn't be any life on Earth. Magnetic field is a barrier for solar plasma. So they bring magnetic field, and around the Earth, so to say, there is an area which is taken by the magnetic field of the Earth. It's the area to 10 or 16 radius of the Earth, and the tail is longer, more than 100 Earth radius. So there is an area which is called the magnetic sphere, and this magnetic sphere always reacts to the pressure of solar wind. So if the changes of the pressure or the solar radiation impact are high, the plasma from the sun can penetrate into the Earth. So you can see such a hole between the sun and the magnetic field of Earth. So the plasma can go inside of this crack, and it creates the aurora borealis, which you can see on the slide. So, as a consequence of that, we have a auroral zone on Earth, and we can see auroral zone in the northern and southern hemispheres on the screen. The difference between them is as follows. The auroral zone is actually determined by the magnetic field of the sun. Magnetic abnormalities do not come to the borders of magnetic sphere. So we have the auroral zone, which is determined by geomagnetic field of the Earth. The geomagnetic field of the Earth is located in the northern hemisphere, where the Greenland is, and in the southern hemisphere in the center of Antarctic. So at the end of the day, it happens so that the polar area in the Antarctic is open to everything and everyone. Our Vostok station is located there, and in the northern hemisphere, it is the area of territorial waters where we are not able to organize any type of research without getting a certain permission. That is the reason why the Antarctic and the area of the polar cap, the station where Vostok is especially important for us. Auroral zone is shifted. And the geomagnetic field is such that in the northern hemisphere, the auroral zone is closer to the border between Canada and the US in night hours. So the impact of cosmic weather there is observed. And they started to actually feel it long time ago. What is this impact about? Problems with radio location, problems with navigation, impact on the pipelines. And about 30 years ago, in the US, for the first time, the devices on nuclear stations stopped to work properly. And the whole eastern part of the US, regions around New York, had complete blackout. So the Western countries started to make such research a long time ago. We started to do it recently when the Arctic area turned out to be very important for us.
Теперь, как проводятся эти...
So how do we actually do this research and forecast space weather? By this, we mean the conditions in the entirety of the around the sun space, but in practical applications, this is limited to our magnetosphere of the Earth. For a long-term forecast, you would be monitoring the solar disruptions, solar flares, which is pretty hard to observe from Earth and measure the angles and directions of the energy. So, in practical terms, the reliability of such forecasts is no more than 50%. Space weather is very important, especially in defense, and people put satellites in Lagrange points. L1 you have here, which is where the distance is more or less equal from Earth and from Sun. Until recently, it used to be just the US satellites. Now there is a Chinese satellite there as well. And these satellites are used for applied forecasts of space weather. And the time frame is half an hour to 90 minutes out. These data are available in Russia as well, where we use it for various practical applications as well. Notably, the first satellite like this, ACE, has almost exhausted its lifetime. Its operation is no longer continuous. It has certain interruptions. But it wasn't managed by a particular agency. So it was in public domain, the data from it from public domain. The replacement satellite still offers open data, but it's under the auspices of the US military, so they can just decide to shut the data off. Bottom left, you can see the propagation of the magnetic field, which is spiral. The rotation of the sun is much faster than that of the Earth. So the data on solar wind that we get from the satellite describe a current of solar wind that can actually go past the Earth, missing it. And in 25 to 30% of cases, the measurements from these satellites, at the cost of billions of dollars to launch there, are things that are not related to the Earth, or only tangentially so. We started doing our research into this in the 80s. Now we've found out that magnetic measurements in the polar caps can give you data to estimate the influence of the solar wind on the Earth. These are the systems of longitudinal currents from the edges of the magnetosphere through to ionosphere. At the center, you have the polar cap. The current goes through that. And at the altitude of 100 kilometers, these currents cause magnetic activity and disturbances on the Earth's surface. If we measure that, we can estimate the solar wind activity on Earth. First experiments were carried out in the 80s at the Vostok station. That proved successful. Then we devised the PC index, the polar cap index. It now has various practical applications. Originally, this was done in cooperation with the Dutch Meteorological Institute. Our counterparts from there, then moved to the Space Research Institute. So we are now in cooperation with the Space Studies Institute. We publish real-time data on PC index. The lag is 2 to 3 minutes. The actual data from the Earth's magnetosphere. Here is an interesting detail. Just recently, last week, there was a major magnetic disturbance. Top right in the slide, you can see the PC index that shows the change in magnetic activity over a day and a half. It went as high as 21, where the normal range is 1 to 2, and beyond 2 you have disturbances in the auroral areas. And here it had the value of 21 millivolts per meter. That meant that the auroral zone was shifted southwards, and this is an image of polar lights made in the south of Russia, in Kislovodsk, just last week, from April 11th. 11th of May, yes. 11th of May. That's a slip of the tongue, sure, of course. New month is upon us, yes. Just last week. And you can see or trace it by the PC index, a real-time measurement, which gives additional input to it. Unfortunately, people in our country prefer satellite data, but the flow of data gets interrupted. People tell us that the operators tell us that sensors were out of order, whereas this index is always available. I have a question. You mentioned the imperfections in foreign satellites. One of them is due to be decommissioned soon. The second one is operated by NATO. And the relevancy of data is around 70%. 25% of data can be irrelevant. If you were to consider an ideal situation, what would be the optimal balance between instrumentation, satellites, or land-based stations, for us to track and predict magnetic disturbances better? Let me finish my presentation and then I'll address your question. After that, we mounted a prolonged campaign on getting the PC index recognized. Now it's garnered international recognition. Our original counterparts who had moved to the Space Research Institute, some people from the Dutch Institute, the Meteorological Institute, tried to actually take credit for that invention. For 8 years, we had to argue our contribution. The index was officially recognized internationally first in 2013 and then finally in 2021. Together with our Dutch colleagues, or Danish colleagues from the Space Institute of the Danish Technical University, we did a recalculation, a back analysis of 20 years, which showed that the index is reliable, and IAGA officially recognized the index as a measure of the solar wind and its input into the Earth's magnetosphere. If it goes up, there are disturbances. Then this same index was proposed as a standard to the International Standards Organization, as a standard for solar weather. It's in high demand now. Came as a surprise to us, actually. We have an open website, and around 500 people visited daily, mostly from other countries. In Russia, it's not as popular. But why would you use our index, our own index, if you have data from American satellites? Well, I'm sure that following your presentation, this website will get much more visitors from Russia. I myself will definitely go look at it. Yeah, it's an open access. Back to my question, please. In the interest of time. Yeah, I'm almost done. Basically, this means that we believe that any organization that operates in the north, which employs radar technology, radio communication technology, simply must use the PC index. All data in the Antarctic are open. Nothing is classified here. We have an agreement with Denmark where we get certain access as well. But then the rules are changing, and there are concerns that the index will close. Under the new rules, we need to pay for the construction of the magnetic station. We need to then also fund the tunnel and other construction, whereas all the instrumentation is already in place. If observation is disrupted for a year, then they might switch to the Italian-French station at Dome C, so that they'll start using their station instead of ours. But the International Association has always supported us. So, still, if the index goes away for at least a year, then we'll get excluded. Yeah, it's a clear case of politics interfering with science and disrupting important research. Let's hope that the negative scenario that you've outlined will not get materialized, and we'll find ways for the Russian index to continue operating. Yes, the most important thing for us is to keep the station operational this year and next year in the old facility under the snow or building the new one. But we don't have the money to do that. That's the thing. Okay. Thank you. Let's move on to the next presenter, Yuri Bubeyev, please. Colleagues, hello. Operations in the Antarctic and in space has always been closely intertwined with medicine. This is due to the unprecedented conditions faced by people there, not familiar in any ways, not suitable for human operation, which posed a problem that needed to be addressed. The advancements in polar and space medicine are complementary. In space medicine, we can see a lot of valuable contributions from the Vostok station in the Antarctic, because it simulates operations on a different planet. There are a lot of data on monitoring physical states, psychological support, which are all very valuable. And the same flow of contributions go from space to the polar sciences as well. Our institute has been mandated with supporting spaceflight, but another important task for us is researching any exposure to extreme conditions. So from 1966, our researchers have been carrying out studies, medical and physiological, at the Vostok station as well. The first stage of that effort took place from 1966 to 72. The main takeaway was that these results were then used to justify extended orbital flights by cosmonauts. The Institute also carried out an experiment which simulated a year-long isolated autonomous operation at a station. So this is a half-contained environment, so to speak, which was done in the Arctic, and the similar features were used to space, like greenhouses, water reused many times, things like that. Human operations and health in the Antarctic and in space share certain features or factors of influence. The first one is limited communications and isolation, then self-sufficiency and lack of access to urgent help in case of accidents or disease, crowded spaces, especially in the older station, unfamiliar parameters of gas environments, small group dynamics with its own rules that apply, and an altered magnetic field as well. Going forward, we plan further research, including at the new Ventran facility. This will include tests of instruments and equipment that we have been developing for similar efforts on the surfaces of the Moon and Mars, elaborating medical and technical recommendations for the furnishing and equipment of the future lunar station, other similar things. As for the basic principles of operating in hazardous conditions, in any such case, you would have four major groups. First is screening for resilience, then preparation for operation in extreme conditions, then if there are any deviations, you need to remedy them, and then after a period of operation in such conditions, you need to ensure prompt restoration or recovery. As for the qualities that are required for successfully performing in such critical situations, you can rely on space medicine as an example. These are people who have high ability to focus and improvise, can survive in small groups, so they have low proclivity to conflicts, they can adapt to extreme situations, they have a positive mindset, even in spite of the situation. And then they need metacognitive skills as well, which basically means an ability to do introspection and reflect on own fears in order to cope with them. We use monitoring in spaceflight that can be applied in polar medicine as well, I think. We will be now transitioning from orbital spaceflight, where you can evacuate, go back down to Earth within a week, provide immediate help, transition to long-range spaceflight, which is kind of more similar to Antarctic operations. This calls for a autonomous diagnostic and correction systems. In space medicine, we have tools to forecast or professional reliability, as we call it, reliable performance. There are methodological techniques for that and instruments. You can do operational prediction of performance failure or incapacitation. Current techniques provide pretty good evaluations. Then there are systems for telehealth assistance in case of injury, for example. Then this includes future recommendations for medical equipment required in long-term isolated operations in order to maintain high levels of professional performance. Promising technologies in this area include miniature trackers that can now be used not only in longitudinal studies like sleep quality, pulse variation, but also in ECG readings of passable quality and measuring of a number of other parameters. There are technologies for evaluating face expressions over a span of 10 seconds virtually. You can make a quick check of the person's conditions and forecast issues with their psyche or reliability in the near future.
Also, different types of audio and visual stimulation with the help of vibro massage devices. Future-oriented is the use of virtual reality and gas mixture on the basis of inert gases. In order to increase workability, they can be used. It's a safe method. And also, I would like to speak about basic technologies, systems that ensure professional reliability of experts working in hazardous professions. So these are devices that can be embedded in the clothes so that experts don't have to spend time making diagnostics. It's done automatically when cosmonauts go to open space, for example. That is exactly what is done. Or there can be methods of telemedicine based on the use of individual data, which increases their value. So it's not average data, not average parameters, but parameters of a specific employee, specific worker. The creation of any team in autonomous conditions follows certain stages. These are the stages of the following types: formation of the group, so it's a working group. Then there is a grouping pseudo-team, where people come together on the basis of their interests. Then next stage is potential team, then real team, and then the final successful stage is the creation of an efficient team. So there is a leader or team lead who knows the stages, and based on such critical moments, he or she can be involved in the work of the team to minimize conflicts, to make sure that the team works coherently with the maximum efficiency. In cosmic medicine, in space medicine, they use methods of psychological support in case of autonomous operation. Number one here is fighting with boredness and psycho-emotional load, so virtual reality can be used for this purpose. There are quite efficient technological solutions which would allow to minimize the negative impact of the above-mentioned factors related to the autonomous operation. In addition to diversity of food, it is important to remember that it's also a means of psychological support. Astronauts, for example, organize such research with pleasure. They try to spend more time interacting with plants, taking care of the space orangeries, for example. And at the new polar station, I think there will be more opportunities to organize such research, to make real contribution to better diversity of food for nutrition purposes. Thank you very much. And I would like to highlight that the Antarctic as well as Men in Space projects are two worlds which are very similar to each other. For example, the first flight of a person to space was on the 12th of April 1961, and in April 1961, at the end of the month, the Antarctic doctor Leonid Rogov made a surgery for himself. It was appendicite. It was like a heroic deed, and no one was able to repeat it after him. Nevertheless, it took place. I think that both space and the Antarctic perceive and receive only the best of the best. And it's such a pleasure to know that these are our people. So, Artemy Yevgenyevich, we would like to hand over to you now. Distinguished colleagues, could you please put up my presentation? Thank you. Good morning, dear colleagues, and I would like to continue the medical and biological agenda that Mikhail Petrovich and Yuri Arkadyevich started today. So my presentation today will be a little bit different from the previous, and because I'm not going to speak only about the nature of the Antarctic, I would also like to get you familiar with the concepts and ideas in the domain of polar microbiology in general. First and foremost, I would like to speak about what is the main idea of microbiological research in the polar regions. To my mind, the ideology is about finding life in areas where it seems it is not available. So this is a wonderful picture made by our colleagues, and here you can see a rock in one of the Antarctic oases, which looks like it's just rock without any life, but you make a small physical impact on it, and then in front of your eyes you can see a wonderful garden, which, as we know today, consists of several thousands of microorganisms. The majority of them are not researched at all. Some of them have ancient roots, and you can study the history of biosphere on the planet on the basis of them. Other can be used in medicine as producers of antibiotics. This concept, this idea of research could not be brought to life if during the 20th century they have not been made theoretical studies and methodological discoveries. First and foremost, at the very beginning of polar microbiology research, and this is the area of biology where we need to thank Boris Lavrentievich Isachenko. So at this early stage of development, it became clear that to study microorganisms in polar regions, you have to go there and do it in situ, as close to the plants, as close to the places where they live. We are followers of this approach, and we support it completely, and we always say that in the larger polar expeditions, there should be polar biologists and, most importantly, polar stations and scientific boats should have necessary laboratory infrastructure to organize microbiological research and tests. On the other hand, it became quite soon clear that the majority of microbiota of polar regions today cannot be grown in the laboratory because there are no conditions to cultivate a wide range of such organisms. That's why the majority of discoveries which were made in the domain of microbiology in the polar regions was made on the basis of genetic material of such microorganisms. By the end of the 20th century, widely spread were metagenome methods. This is when experts and researchers study the genetic material received from the area of habitat. You can take a sequenator with you to the expedition. It's quite cheap, and you can identify preliminary certain microorganisms, or you can even make sequencing, which means the reading of the plant's genome right in the time when you are in the camp. So here on the slide, you can see the process of the sequencing in the Arctic dry valleys. It's made by the Oxford University. So such research led to a breakthrough in the polar research of microorganisms. Microbe communities in the polar regions are not worse, if not better, in terms of biological diversity than the ecosystems in the tropical regions. It's interesting that this diversity is created by live organisms, which on the basis of experimental data can have metabolism and develop in such extreme environments as the snow in the Antarctic. Quite developed communities in the Antarctic are described, even though they are in the central Antarctic, in the area of polar plateau, Antarctic plateau. That allows us to research cryogenic areas of the Antarctic as a huge resource base, which is not well researched right now. But this is the area where you can search for useful organisms that can synthesize biologically active substances. On the slide here, you can see several examples of the use of bacteria from the Antarctic in different areas of economy. Actually, we don't always understand how much polar microbiology can give us, from the production of ice cream to the open heart surgeries where cryoprotectants are used. But these are the substances produced by polar bacteria. Right now, quite efficient methods of screening are developed where you can search quickly for bacteria that can synthesize new antibiotics or act against tumors. Here on this slide, you can see the research made by our group right now. We are trying to create a new antimicrobial substance, which most probably will be used as disinfectant. It's a live disinfectant, and you can use it in hospitals, in medical facilities. So this kind of substance will consist of Antarctic bacteria, which were found in the eastern part of the Antarctic. It is clear right now that among such microorganisms there are bacteria that can produce antimicrobial peptides, and thanks to the production of such peptides then can suppress the growth of bacteria that are resistant to traditional antibiotics. One more important side effect, so to say, of this huge biological and genetic diversity of the polar microbiota is as follows. In polar regions, the natural infections can happen in high altitude. because the birds can transmit such infections, and the infection course or centers of infection can happen in the Antarctic. So right now we are describing a new type of pathogenic bacteria. Here we are working together with the Institute of Epidemiology named after Pasteur. So you can see that even in faraway ecosystems, in the land of Franz Josef, there is a circulation of infections and bacteria which are interesting from medical point of view. On the other hand, we can see that polar microsystems are points of attraction for thousands and sometimes even millions of birds, and they are, so to say, places where microbiota is exchanged between animals, and these are places of generation of new viruses, types of microorganisms, which are dangerous from the epidemiological point of view. On the slide, you can see a part of the study which is made by us together with our colleagues from Novosibirsk organization Vector. This research was focused on influenza A virus. So on quite a small area of King George Island in the west of Antarctic, we found influenza A virus. Based on the material represented on the slide, you can see that at quite a small territory, at the same time, several types of genotypes of influenza A virus can circulate, including H1 and H3N1, which caused the Spanish flu epidemic a long time ago. So what is especially important for us? The aspect of our research that shows that we need to have focused and long-term places to have monitoring, for us to be able to monitor the formation of new types of dangerous virus in real-time mode. We can see that the polar ecosystem, as far as this question is concerned, is truly interesting. So here you can see examples of how new genotypes of virus happen because of the exchange of genetic materials between different representatives of polar fauna. So now, finishing my presentation, I would like to touch upon some aspects related to the global climate change. As it was already mentioned during our conference today, the climate changes are especially vividly seen in the Arctic and Antarctic. So this is the risky territory related to the climate warming, and there are biological risks which are absolutely real today. Just to illustrate this saying, I want to say that there was, for example, Siberian anthrax in area where animals who died of Siberian anthrax were buried. So the material traveled to the areas where deers live, and it was quite a difficult epidemic. About 100 people were hospitalized, several people died in the result of this epidemic because of their special nutrition. And Siberian anthrax is the disease that epidemiologists have known for a long time. There are vaccines, it can be prevented, there are antibiotics which allow to fight against this disease. But permafrost in the polar regions, including the Arctic, can hide a lot of microorganisms that we know little about. So the works where our laboratory was involved in the Institute of Experimental Medicine demonstrate that in permafrost of the Arctic and in the mummies of animals, bacteria are still alive, as well as viruses that can be recultivated and introduced to modern ecosystems. This allows us to come back to the previous topic and to continue to discuss how important it is to prevent risks related to the dissemination of ancient infections, and taking into account that this problem was discussed at the highest level hearings of the State Duma. Thank you very much, Arseniy Yevgenyevich. We see that the real threat is there. Related to the distribution of dangerous diseases due to the global warming. You have noted that in the Arctic and Antarctic, the organisms, ancient organisms were found which were still alive. So it is probable that if the global warming continues, an ancient virus can come out which we are not aware of, and we will have to deal with it. So thank you very much. And I would like to hand over to Dmitry Chechin.
Добрый день. Спасибо.
Hello. I would like to thank the organizers for this opportunity to speak at this conference. I represent the Laboratory of Ocean and Atmosphere Interaction at the Obukhov Institute, and I would like to tell you something about our most recent research. The title of my presentation contains the name of the Arctic, whereas this panel is on the Antarctic. This seems to be a contradiction, but the same processes take place at both of the poles, and some of the processes are potentially more relevant for the Antarctic than the Arctic, actually. One of the subjects addressed at this conference is the importance of weather forecasting and climate modeling in polar regions. Let me start with a potentially provocative statement that if you are to have a good solid model of weather or the climate system in the polar regions, then the key is to properly simulate the boundary layer, which is the layer of atmosphere which interacts through turbulence with the underlying surface. It seems to be pretty narrow. It only transmits heat and pulses between the two media. But it has been established now quite clearly that in this boundary area there are a lot of different processes characterized by very different physics. They all play an important role in the climate system, and the weather that we can see with our eyes is formed in the boundary layer. It generates fog, clouds, precipitation. It facilitates emission of aerosols from the ocean. It enables the drifting of ice. So weather proclivity is generated by the boundary layer as well, like low visibility, generally bad weather, you name it. So for us to improve our weather forecasting, especially at the poles, we need to study the boundary layer more and model it to a new level of perfection. This poses a problem. Addressing the boundary layer means that we need to specialize not just in turbulence-based exchange, but also in all other types of physical processes that are inputted into the model. This includes near-surface layer, microphysics of clouds, radiation aerosols, turbulent diffusion, a whole host of things that interact among each other in a very complex fashion. It's a small task for us, researchers of the boundary layer. It can be simplified a bit. You can review isolated types of boundary layers or its conditions. So my presentation is going to focus on some typical instances of boundary layers in the polar regions. I'll tell you about the current issues and studying their conditions, as well as how our research addresses those, how this can be translated into weather and climate models. First, I'll talk about the convection type boundary layer. I'm sorry, can you give us a bullet point view because we are running late, if that's okay? Sure. Here is the bullet point view. This is the layer which is heated from below. You have it in the Arctic and in the Antarctic, above the ocean surface exposed, free from the ice, when cold air arrives. The largest example is marine cold intrusions that you have at the poles. Most recent research has shown that the most pressing issue here is to simulate the phase composition of clouds, as well as the parameters of clouds, for example, the cloudiness core. The sensitivity of climate models to forcing of greenhouse gases is determined, among other things, by the veracity of the model in terms of the phase composition, especially in the south, where you have cyclone fronts with cold air from the Antarctic going to lower latitudes. Here is an image of a cold intrusion. That's the Barents Sea, the Norwegian Sea. Sorry, audio is out. Still no audio feed, apologies.
Hello, yes, I can hear you. Yes. Okay. This is just a try, right? This is a test, just a test. Okay. Okay. Can you see? Uh, yeah, just a moment, just a minute, just a moment. Is it okay? Okay. Okay. So,
1, 2, 3, 4.